So today we're going to be learning about how you can look at a polynomial and figure out a few different things that can be crucial. So first I'm going to be giving you a example polynomial. The p of x is equal to x to the fourth minus 2x to the third plus 5x squared minus 8x plus 4. So here's our polynomial. Just looking at this leading coefficient, we can figure out a few different things. The first thing we can learn about is the end behavior. Second thing is the max number of turns. And the third is the minimum number of rational roots. Rational roots. Not complex, not imaginary, rational roots. So as far as end behavior, we can say, okay, x to the fourth. Is this even or is this odd? 4 is an even number, so therefore the end behavior is going to be going in the same y direction, but opposite x directions. You can also see this in a x squared equation, because it's going to be a parabola. So again, the same y direction, opposite x directions. And this goes for every even degreed coefficient, leading coefficient. It's just going to get broader and broader as it goes, x to the 6th, 8th, 10th, whatever. It's just going to be the same y direction, opposite x direction, just broader. So that's end behavior. Max number of turns. So we can see x to the fourth. Let's look at x squared again. A parabola. How many turns did it have? 1. Let's look at x to the third. 2 turns. So basically what you can get out of this is if we look at our leading coefficient and we look at the degree of it, in this case 1x to the fourth, we're just going to subtract it by 1, and that's going to be the max number of turns. So max number of turns is 3. Let's write that in. End behavior is going to be that. Next is the minimum number of rational roots. Rational roots. So if we look at this again, x to the fourth, or if we look at x to the third or x to the second, this is just going to tell us how many this is just going to tell us how many roots we have. So x to the fourth, we're going to have 4 roots. X to the third, 3, etc. So that's how we tell max number of roots. Okay. Now we're going to be looking at the domain and the range of this equation. Well, actually, we can say that for later because it'll make more sense with the range. So I guess next what we'll do is finding the possible roots. And basically, this is going to be a theorem, which tells us that P over Q is going to give us our rational roots, which is just kind of an equation. And the P is going to stand for, well, I'll actually visually show you so it makes more sense. I'll give you this again, or I'll write it up here. P of x equals x to the fourth minus 2x to the third plus 5x squared minus 8x plus 4. So how are we gonna know what's P, what's Q? This is how I remember it, is quarter pounder. So we're gonna look at the P value, the Q value is gonna equal 1 because the leading coefficient is 1, and our P value is gonna be 4. Our constant is 4. And what's important about this theorem is to remember that we need to find the factors of both of these numbers. The only factor of 1 is 1. The factors of 4 are 1, 2, and 4. And we're going to put plus and minus because there's going to be 6 possible roots. And this actually imposes a fraction. So we're going to have plus or minus 1 over 1 plus or minus 2 over 1, and plus or minus 4 over 1. And those are our 6 possible roots for this polynomial. So now that we have found our possible roots, which I can put over here, possible roots, 1 plus or minus, important to remember plus or minus. We have our 6 possible roots, and now we're going to find, attempt to find the complex roots of the polynomial. And this is where the whole process gets a little bit tedious. So first we're going to look at our coefficients only of our polynomial that's given to us. So we're going to have 1, negative 2, positive 5, negative 8, and positive 4. And so we're going to test all 6 of these roots to see which one gives us a remainder of 0 through the process of synthetic division. So let's start with 1. We're going to bring down this 1. 1 multiplied by 1 is 1. Negative 2 plus 1 is negative 1. And then we're going to get negative 1 up here, and we keep repeating this process until we get here. Positive 4 minus 4 cancels out, so there's no remainder, which means that x equals 1 is a root. Is actually a rational root, because this root is not imaginary, it's not complex, so x equals 1. So what this gives us, the synthetic division gives us, is a reduced polynomial. So instead of having x to the 4th, which was eliminated, we now have x to the 3rd minus x squared plus 4x minus 4. Here's our new p of x, our reduced polynomial. And our goal here is to take this polynomial, find another root, reduce it again, until we get a quadratic, which we can then find the rest of the roots through the quadratic formula. So we can take this, do synthetic division again, 1, negative 1, positive 4, and negative 4. And let's just try 1 again. And we go through this entire process again. So we're going to get 1, 0, 0, 4, and here we go. Cancel again. So that means x of 1 is a root. Again. So there's 2 x of 1 roots, which is then we get it to multiplicities, which I'll explain later. So the important thing to remember is that x of 1 is a root of this polynomial twice. So there we can write x of 1, we can just write here, we'll write roots. X of 1 twice. X of 1 is a root twice. So now we're going to go back to that quadratic that we just reduced. We reduced the reduced polynomial, we reduced again to make a quadratic, and that quadratic was x squared plus 0x plus 4. That's our new quadratic. Okay, so we're going to factor this. I guess you can factor this, but we can also use the quadratic formula. Using the quadratic formula will give us the other 2 roots. And how we do this is we come up with an a, which is going to be our first variable, which is a 1. B is 0, and C is 4. A, B, C. That's how you find that. And the quadratic formula is going to be, the quadratic formula is negative b plus or minus the square root of b squared plus, minus 4ac over 2a. Okay, so we're going to take these variables and we're going to plug them in. So we're going to have negative 0 plus or minus 0 squared minus 4 times 1 times 4 over 2 times 1. And that comes out to be our x, 1 and 2 is going to be equal to 0 plus or minus the square root of 16 over 2. And negative 16. And the square root of negative 16 is going to be an imaginary number. Okay, it's going to be a complex root. So the normal square root of 16 is 4, as you know, so it's going to impose a 4i. It's going to compute to a 4i, and we're still going to divide that by 2, so we get a 2i. And we got to recall that we have a plus or minus, so this is going to be either a positive 2i or a negative 2i, which are the two complex roots. So we have just found the two complex roots. We'll rewrite up here. X equals negative 2i and x equals 2i. Okay. Now that we've found the complex roots, we can go back to multiplicities, which I was kind of brought up earlier. Here we have our roots. X equals 1 twice, x equals 2i, and x equals negative 2i. So we have two roots that are the same. That just means that, well, here, let me write this out better. 0 equals x, or sorry, x equals 1. We want to get x and this number on the same side, so we have x minus 1 equals 0. So that's our factor. Okay, so we have x minus 1 squared, and this is going to be called our multiplicity. And I'm not just going to say that's our multiplicity, I'm going to kind of explain to you what a multiplicity is. And a multiplicity is this. Graphically, it is this. So the first degree of multiplicities, it just means that it's a straight line. It's going to go straight through the x-axis. The second multiplicity means that our graph is going to touch the x-axis. It's not going to go through it. It's not going to stay on the x-axis and continue there. It's going to just touch it. A third degree multiplicity is going to be like an s, almost like a third degree polynomial. And just getting on to more like 4, 6, 8, or 5, 7, 9 multiplicities are basically the same as what you see here, except just broader. Okay. So now that we know about multiplicities, we can say, okay, so x of 1, or the root x equals 1 is repeated. So we have x minus 1 squared. So what does that mean? That just means that our graph is going to somewhat look like it's going to touch. So we know that the graph looks like that because we know the end behavior, and we also know the multiplicity that's just going to touch the x-axis. It's not going to go through it or anything like that. So this just basically gives us an idea, a visual representation of what our graph is going to look like. So next is the x-intercepts. The x-intercepts are going to be our roots. We're going to look at our roots, and we have x equals 1, and then another x equals 1, and then also the complex roots. And x-intercepts cannot be complex, so therefore we only have one root. We only have one x-intercept, which is going to be this. X equals 1 is our only x-intercept. Again, because complex roots are not x-intercepts, and we have two the same one, which will just give us one x-intercept. So visually, we'll go back to our visual representation. Here's 1, which is our x-intercept. We can look at our equation again and see here we are, our y-intercept, which is 4. So we know that. So we know it's going to look something like that. Something like that. And our last thing we're going to be talking about is writing this polynomial in factored form. Factored form. What is factored form? It's basically just taking your roots and instead of them being roots, we'll find them as factors and we'll put them together, and that'll basically give us our equation. Just looking at factors though instead. So I'll show you p of x we're going to take our, well, first we can just look at our roots. Actually, we'll just first look at our roots. X equals 1, x equals 1, x equals negative 2i, and x equals 2i. And basically, we're going to take that multiplicity again. Or here, I'll show you. X equals 1, we're going to get these things on the same side, so x minus 1 equals 0. We're going to do that for all of them. So here's our factor. Not our 0, but our factor. So p of x equals x minus 1 squared. And then we're just gonna, we can take these, I could show you in these two. So x plus 2i equals 0. But it'll just end up being the same thing because we have a positive 2i as well as a negative 2i. So x minus 2i and x plus 2i. And here's our factored form. So just to review, oh, we still have to do our domain and range. Because I said I'd save that for later. Our domain and range is going to, well, first we'll discuss what the domain and what the range is. The domain basically just tells us what is left to right and what is bottom to top. We're talking about our basically how far out our graph is going. What are the limits of our graph, basically, is one way you can put it. So the domain, we can say, okay, we have an x to the 4th graph. So we recall that it's going to be going in opposite x directions, but the same y direction. So we know that we don't have a limit on our x direction. So left to right, we're just going to have our domain is parenthesis negative infinity to positive infinity parenthesis. And I'll explain the parentheses in a second. In the range, we're going to have 0, because if we looked at our graph, it was 0, 0, 1 actually is where it should be, and 4. Whatever, this is just a rough sketch, but we have 0 as our bottom of our graph, and the top is infinity because it's undefined. A bracket just tells us that we have a defined value, and a parenthesis will tell us that we have an undefined value, such as infinity, because it keeps going and we're not exactly sure what that value is. So we use a parenthesis to indicate that. So, alright, that's how you look at a polynomial and find those 9 different things. And yeah, I guess we can just review what we learned. We basically learned to describe the end behavior by looking at the leading coefficient's degree. Also looking at the degree, we can find the max number of terms and the minimum number of rational roots. We found the domain and range just now. We used the rational roots theorem, which was P over Q. No absolute value, it's just like that. We found the complex roots. We stated the multiplicities, what they mean for just touching. And we found the x-intercepts, which was just one of them. And we wrote it in factored form.